Sorry, I forgot to hit record.
Thank you.
That's fine. Thank you for reminding me. Thank you. So, like I was saying then, okay, when it comes to calculating the electric field due to a dipole, okay, and again, I just drew this dipole you see here, and we said a dipole is just a shift between center positive charge, center negative charge, giving rise to this dipole moment. And this dipole moment, right, will generate an electric field at a point in space P, and this electric field, okay, at this point P, in space, okay, at the distance x1, will be given by this expression. Electric field E1 equals a 2k mu over x1 cubed. Now, what happens if the distance happens if the distance is double? Okay, if I double the distance, which means x2 now is equal to 2x1, what would happen to the electric field E2? Okay, so that's what the question is asking us for. Now, my starting point then will be E1, electric field 1, okay, for a point in space at distance x1 will be 2k mu over x1 cubed, and then E2 now, right, I'm going to use x2. That's the only thing going to change. Now, x2 is 2x1. x2 is 2x1. I just substitute that. And cubed, you'll end up with 2 cubed times x1 cubed. Now, 2 cubed is 8. You end up then with a factor of 1 over 8. Of course, the rest you keep it as 2k mu over x1 cubed. And what is this? All this is just, of course, the expression of electric field for the point in space at distance x1. So all we end up with then is the following. So electric field then E2 is equal to 1/8 E1. So the factor will be a factor of 1 over 8. Okay, I hope it's clear to everybody. Okay, so let's clear these notes and move to the next question. The last question in this midterm 2019. Now, this question is asking us the following: a proton moving, okay, at a certain velocity v naught. Okay, let's highlight some of the parts. So V naught enters a region between two parallel plates with charge densities of sigma. So we're given the charge density, sigma equals to 2.8 10 to the negative 9 coulomb per meter squared. Okay. Now here you see the charge density is in coulomb. Okay, coulomb per meter squared. Calculate the electric field E in the region between the plates. We're giving you epsilon naught permittivity of free space. Okay. Now, all I'm asked here is to calculate the electric field between two charged parallel plates. Now, for two charged parallel plates, remember we saw this in the lecture. When you have two charged parallel plates, one is charged positively, the other is charged negatively. The electric field E is just the charge density divided by epsilon naught. That's all we need to use. And we happen to have the charge density in Coulomb, already in Coulomb per meter squared. We had a question like this, if you remember in the lecture, where it was in microcoulomb. We have to convert to Coulomb. Here, no need to convert. It's already in Coulomb per meter squared. So all we need is to plug the numbers in. Okay, so this is the charge density divided by epsilon naught. You end up with this value of electric field. Okay. So that's all for this midterm 2019. I hope it was all clear, okay, to you guys. Now what we will do is we're going to go to midterm 2018. Right here. 2018, or was it again? 3. Saved it here. Let me double check. Second. So 2018, where is it? Second, guys. I did not save it here, so what I'll do is I'll go back to the page. Okay, 2018. Just 1 second. Now, can you see the questions, guys, from midterm 2018? Yes, you can. Okay, that's great. Now, what we will do, because we've been answering questions related to chapter 16, and because we also have answered, okay, the questions related to the previous chapters. Now, I'll probably go in reverse order. Okay, so I'll start from the last ones, okay, and I'll be moving backwards. So question 20, the last question in this midterm, okay, the last question in this midterm will be the following: nerve membranes in the human body are best modeled. There's a typo here. So are best modeled, okay, as a system, of course, of charged parallel plates, right? So this is the answer to this question, like we saw in the lecture. Question 19, the combination of two separate point charges of opposite sign but equal magnitude is called an electric dipole. Now, it's more like we said, a shift between center of positive charge and negative charge, rather than 2 point charges. But anyways, you get the idea. Okay, so this is then an electric dipole. Now, question 14. Question 14 says the following: 4 charges are placed at the corners of a square as shown in the figure. Now, the direction of the electric field at the center of the square will be in which, or following which direction? Is it P, Q, R, or S? Now, let's look at the charges. I'm going to use the pen again. It's working today. So here, I'll start with charge Q1. So you see we have Q1 here, Q1, and then Q2, Q3, and Q4. Okay. Now start with Q1. So for Q1, okay, now I'm dealing with a positive charge. I'm dealing with a positive charge. And keep in mind, the question is asking you for the direction of the electric field, direction of electric field. Now, before I look at the direction of electric field for these 4 charges, just as a reminder, can you tell me when you have a positive charge plus Q here, and you're looking for the electric field at any given point in space? I'll use a cross. Okay, I'll use a cross to signify this is a point in space. You don't have to have a charge in this point, so it's just a point in space, right? And you want to know what is the magnitude of the electric field at that point in space. It's like you want to know what is the magnitude of the magnetic field strength at a given point in space. So you don't need to have another magnet in that point in space. So it's the same thing here. So it's a point in space. Okay, and you want to know what is the magnitude of electric field, and also the direction. So when the charge is positive, can you remind me, what is the direction of the electric field at this point P in space? Is it going, how is it going? It's going, Tanya, lean outward. Very good. So here, the electric field is going outward away from the charge, like this. So this is the electric field for a positive charge. Now, if I'm dealing with a negative charge, like this, let's say this is minus Q, negative charge. And when I look at the point in space P here, point in space P, the electric field will be, can you remind me, guys? The electric field will be, in this case, inward towards the negative charge. Inward, like this. A positive charge outward, negative charge inward. So I'll do just that. Now let's start with Q1, like we said. So starting with Q1, at point P, or at the center of the square, I'm here. Now the electric field due to charge Q1 will be this electric field E1. See E1? That'll be my electric field caused by charge 1, and it's going outward away from charge 1. I hope it's clear to everyone. Now, moving on to charge number 2. Let's go to charge number 2. Charge 2 is a negative charge. It's a negative one. Now, a negative charge means the electric field is going inward towards the charge. So it will be this vector E2, this vector E2, pointing inward towards charge E2. And we repeat the same exercise for charge Q3. Now Q3, I see it's a positive charge. So Q3 will generate an electric field E3 that is pointing outward away from the charge. So E3 outward away. And the last one, Q4 is also negative now. Q4 is negative, and it's going to be inward towards the charge. So Q4 will generate electric field E4. Here it is, E4, and it's inward towards the charge. Now, these are the electric fields, okay, for each one of these 4 charges. Now, of course, the sum total would give us the total electric field. Now, you notice I have E2 and E3, okay? The sum of these 2 vectors will be this bigger blue vector, okay, this one here. And the sum of the 2 vectors, or the 2 electric fields, E1 and E4, the sum of the 2 will be this also bigger vector electric field, which means the total electric field will be the sum of these 2 blue vectors. When you add them up, you end up with this vector sum. Okay, so the total electric field E, which is the sum of all electric fields, E1 plus E2 plus E3 plus E4, all 4 vectors, of course, in vector notation. Forget it's in vector notation, okay? So that will be then corresponding to the vector P. So the sum total, or the total electric field, okay, and that's corresponding to option A, is shown by arrow P. I hope it's clear to everyone. Okay. Right, so that's question 18. Okay. Let's move backward. So, question 17. Now, question 17 says, I hope you can still hear me from there, guys. Let me know if otherwise I'll speak louder. Yes, you can. Okay, that's great. So here, question 17. The electric field of a point charge has an inverse what behavior? Of course, it's an inverse R squared behavior. Now, here the only thing is the question is asking about electric field. Okay, while here you see force, but that's okay. We're still can turn this into electric field. That's a typo. And instead of two charges, remember for electric field, we only need one charge. Okay, so just remove one charge. And we're dealing with one charge generating an electric field at any given point in space. Okay, but still the variation has an inverse r squared behavior. Right, okay, so that's question 17. Question 16. We have an electron with a charge. So it's an electron with a charge value of 1.6, 10 to the negative 19 coulombs, is moving in the presence of an electric field of 500 newtons per coulomb. Okay. What force does the electron experience? Now, of course, in this case, it's just asking for the magnitude of the force. It's not asking about the direction. Okay. The question here is not asking about the direction. Unlike the question from midterm 2019, you remember the last one we did last time, which was question 18, I think. So question 18 from 2019, I'll show it to you now. We're done with this one. So in that question, we only had to calculate, or in that question, we had to calculate both, or to give both the magnitude and the direction. Here, we only need the magnitude, so we're using force is equal to charge times electric field, okay? So the charge, okay, the absolute value of the charge, even though it's negative, I'm taking it as positive 1.6 10 to negative 19, and then multiply by my 500, my electric field, which is 500 newtons per coulomb, okay? Now, if you're given the electric field in volts per meter, do not panic, it's the same thing, okay? It's going to be the same thing. No need to change anything. So all you need then is plug these numbers, okay, in your calculator, and you get this value of 8, okay, 8 times 10 to the negative 17 newtons. So this will be the magnitude of the force. It's not asking about the direction, okay? Now, if I, for example, gave you an electric field that is pointing, for example, right, in this way, and then I'll tell you, like in the question, so we're dealing with an electron, and you know that for an electron, the charge is negative 1.6 times 10 to the negative 19. And I ask you, okay, and I ask you also for the direction. What would be the direction of the force? If the electric field is pointing right, what would be the direction of the force? Will it be right or will it be left? What do you think? Can you tell me, guys? So it will be opposite. Okay, Mustafa? Yes. Here it will be opposite. Yes, left. Very good. So if the electric field is pointing right, the electric force will be left because I have a negative sign, okay, for the charge. So you need to, for the direction, you need to multiply the direction of the electric field by the negative sign, which will give you the opposite direction, okay? But that's not what the question is asking you here. It's just asking for the magnitude. But if I take you, just as a reminder, if I take you back, this is 2019. That was question 17, so I thought it was 18. If I take you back to question 17 from 2019, we did last time, okay? You see it's asking for both. It's asking for both the magnitude and the direction, okay? And because we were dealing with a negative charge, see here, it's a negative charge, and you see the electric field was pointing left, okay? Electric field was pointing left, and the force here is pointing right, this force. So again, it depends what the question is asking you for. Let's go back to midterm 2018. Now we're done with question 16. Okay. Question 15. Question 15 says, if we double the charge on both the 2-point charges and double the distance between them, how much does the electric force between them change? Now here, if we're starting with two charges, Q1, Q2, and the two charges are at a distance, let's call it R1, okay? This will give me a force F1, between the two, which is K Q1 Q2 over R1 squared. Now, if I double both charges, which means I have 2 Q1 instead of Q1, and here I have 2 Q2, and here I have also double the distance, which means 2 R1. Okay? Now, what would be the force F2 in this case? What would be the force F2 in this case? That's my unknown. Now, in this case, F2, I would write it as K. Now, the charge I'm dealing with would be, or the charges will be 2Q1, 2Q2, and the distance will be 2R1, which I have to square. Now, upstairs in the numerator, I'll have 2 times 2 will be 4. Downstairs, it's a 2 squared, will also give me a 4. Now you can see the 2 4s will cancel each other. You end up with KQ1, Q2 over R1 squared. And what else is this but F1? So F1 then, okay, would be what I end up with, which means force 2 will be equal to force 1. And that means the force remains unchanged. It will remain the same. So the force will remain the same. Okay, when you double the charge for both, okay, when you double both charges and you double the distance, the force will remain the same. Okay, hope it's clear to you guys. Now going backward to question question 14. Now I'm going back to chapter 4, or sorry, chapter 9. Okay, so we're done with questions related to chapter 16. We're going back to questions related to chapter 9. Now, the question is asking you for this. A fixed mass of gas initially occupies a volume of 1.4 liters. So I'm starting with an initial volume V1 of 1.4 liters at pressure P1 equals to 4.4 atmospheres. That's my initial pressure and initial volume. If the system is expanded, I'm told the system is expanded. Always try to highlight the keywords in the problem. Okay, always look for the keywords. So if the system is expanded from an initial volume to final volume, final volume is 4.4 liters at the pressure P2 of 1 atmosphere, along path AB. Now calculate the work done on the gas. Calculate the work done on the gas, and we're highlighting also the keyword on, okay? The work done on the gas along path AB. Now we're also giving you 1 atmosphere is 101.3 kilopascal. Now, of course, you'll remember from the questions related to this chapter, okay, that in order to calculate the work, okay, all you need is calculate the area under the PV diagram, okay, or the PV graph. So here I'm dealing with this linear relationship between pressure and volume, and we're going from A to B. So we're following this path, A to B. This is my initial volume, this is my final volume, and I'm told, okay, the system is expanded, and you can see it. Volume is increasing, which means I'm dealing with an expansion. I'm dealing with an expansion, which means the work should be counted as, can you tell me, positive or negative? So if I'm dealing with the expansion, can you remind me, guys? Yes, Tanya, negative. Very good. So here, because it's an expansion, work will be negative. Okay? Very good. See, so work is negative in this case. Now, and it's how do I calculate this work? Is by calculating the area under the graph. So now you can see I have two parts. I have a rectangular part and I have this triangular part too. So here we need to calculate the areas from both and then add them up. And then my work, the total work, will be, I'll assign a negative sign to it. Okay. So here, then I'll start with the area for the rectangle. The area for rectangle will be base, okay, the base times the height. Now the base is what? The base is V2 minus V1. The height is just P2. I hope you all agree. Now here then, I'll call this A rectangle. Area rectangle is equal to base, which is V2 minus V1 multiplied by P2. Okay, I hope you all agree. And it's equal then to, if I plug in the numbers, my final volume is 4.4 liters. 4.4 minus 1.4 liter initial volume. That's my delta V, okay? Multiplied by P2, and P2 is 1 atmosphere. But I'm not using atmosphere, I'm using kilopascal. Now, question, you're saying if it says in here, work done by the gas, it will still be negative. Now, I'll come back to that question, Tanya. Okay, so let's first see how we calculate this work, and then I'll answer your question, Tanya, if you don't mind. Now, here then, so we have area rectangle. Again, this is the base, okay, delta V, times the pressure, which is 1 atmosphere. But 1 atmosphere is what? In kilopascal. So I use kilopascal. Remember, when it comes to the units, okay, when it comes to the units, we said that kilopascal, okay, go hand in glove with liters. When you have pressure in Pascal, the volume should be expressed in liters. When you have Pascal for the pressure, the volume should be in, can you remind me? The pressure is in Pascal, the volume should be in cubic meters. Yes, Tanya, very good. Okay, so pressure Pascal, volume cubic meters, pressure kilopascal, volume in liters. So because the volumes are in liters, it will be easier to keep the pressure now in kilopascal. Now P2 is 1 atmosphere, and it's equal to 101.3 kilopascal. So I'll use then 101.3 kilopascal for the pressure P2. So this will give me area rectangle. Now, how about the area for the triangle? For the triangle, remember, it's a half. Okay, the area is 1/2. So let's call it area. Let's call it area triangle. A triangle. A triangle equals to 1/2. Now it's the base, same thing. V2 minus V1, it's the base, times the height. Now you see the height is going to be P1, the highest value, minus P2, which is the lowest value. It will give you then the height of this triangle. So that will be P1 minus P2. Now, same idea, I'll plug in the numbers. So it'll be 1/2, final volume 4.4, minus initial volume 1.4, and then multiplied by P2, P1, sorry, P1 is 4.4 atmospheres, 4.4 minus 1 atmosphere. But we don't keep the pressures in atmosphere. We have to multiply them by 101.3 in kilopascals. Okay? I hope it's all clear. Now, this will give me the two areas. This will give me the two areas. Okay? Yes, Mariam, yeah, very good. So I didn't see that. Here. So the work then, the work, let's put it in blue now. Let's change color, maybe in purple. So the work done will be, I'll put a negative sign. So it will be equal, work done will be equal to minus, okay, minus the area of rectangle, minus area of rectangle plus area triangle. Area triangle. Okay, so this will be your work done. In this case, I know it's negative, okay, because it's going to be a work corresponding to an expansion. So it's negative the area of rectangle plus the area of triangle. Okay. Now again, this is work done on the gas. Okay, this is work done on the gas eventually by you. So that means, again, if you look at the gas chamber like this with piston, and you are here trying to push this piston like this to the left, okay? But in this case, the work or the piston is not following your force. The piston is moving in the opposite direction. This delta x is opposite the force you're applying. Now, so the work you are doing, okay, trying to compress the gas, isn't working. Okay, so it's the gas who is doing the work now. Okay, so that's why work done on the gas is negative. But like you said, Tanya, I think you were asking the question, Tanya. So you said, what if then we look at the work done by the gas? So work done by the gas would be the same value, but it will be taken as positive. Okay, be the same value, but taken as positive. Now, yes, Faisal, can you remind me later about the attendance? Yes, also, I think, who is that again? Can you remind me, guys, about the attendance towards the end, right? Okay, I hope it's clear to about the question. So the next steps, I hope it's all clear about the question here. Let me delete these notes. There will be anyways in the recording. That is, this. We're going to repeat the same thing, okay, in the notes already. So this is then, these are the same steps. The work is minus yellow area plus blue area. And then you see this is the area of the triangle plus the area of rectangle. Okay, and plugging in the numbers, you end up with this value, which corresponds to negative 821 joules. Okay. Great. So let's carry on quickly before finish questions. Now, question number 13. Question 13. I may take 5 more minutes from you guys if you don't mind. So question 13. Question 13 says a thermodynamic system undergoes a process in which its internal energy, so internal energy we're saying increases, so keyword increases by 5,000 joules, mean change in internal energy delta U, because it's increasing, okay? Yes, Mustafa? Yes, Mustafa Hilal. Yeah, your question, P1 minus P2. Why did I do P1 minus P2? Because I just want the height. It doesn't matter which one is final, which one is initial. I just wanted the height, okay? The height of the triangle. So I did that, okay? So here we're saying delta U increases by 5,000. That means I take plus 5,000 joules, okay? Plus 5,000 joules. In the process, 9,000 joules of energy leaves the system. So keyword here, leaves the system as heat. So because it's leaving the system, so Q will be taken as negative 9,000 joules. Now find the work done on the gas. So work done on the gas. Okay. Now in this case, I'm dealing with a thermodynamic system, and I'm using first law of thermodynamics, delta U equals to heat exchange plus the work done. Okay. And in the first law of thermodynamics, I'm assuming the work here is work done on the system. When I put the plus work, I'm assuming it's work done on the system. Okay, it's work done on the system. So here, if you end up with a positive work, if, let's say, if work you find is positive, that means it's work, the work is done, okay? The work is done, the work is done by you, okay? So that means you are doing the pushing. If the work is negative, the work is done by the piston, okay? So that work is done by gas. The work is done by gas, all right? So the work is taking over, so it's stronger than you, so he's doing the pushing. So, but here I'm assuming then work done on the system in the formula. So if you find it as positive, yes, it's done by you, okay, on the system. If it's a negative work you find, it's done by the gas, okay? Now, here you plug the numbers in. 5,000 is equal to negative 9,000 plus work. That means you end up with a work that is positive 14,000 joules. Okay, that's 14,000 joules. This is option B. I hope it's clear to everybody. Now, question number 12. A 2-mole ideal gas system is maintained at a constant volume of 40 cubic meters. Keyword constant volume. So constant volume means ISO. You remind me, guys? How do we call a process that is happening at constant volume? We call it isochoric. Yes, Faiza, Anin, so isochoric process. So that means when it's isochoric, okay, what happens to the work? The work will be 0. Very good. So work for isochoric processes is 0. Why? Because the piston doesn't move. Okay, the volume doesn't change, the piston doesn't move, no work is done. So here, if 100, we're saying if 100 joules of heat is added, keyword added, what is, that means Q here is counted as positive. Heat will be plus 100. So I take it as positive. So we're asking you, what is the change in internal energy of the system? Again, first law of thermodynamics, delta U is equal to Q plus work, heat plus work. Now the work is 0. Okay, so you end up with delta U equals to 100 plus 0, which is 100. What does that mean? It means that all the heat I am adding to the system will contribute into to increasing the internal energy. Okay, so that's all that's happening in this case. Now, isobaric isn't constant pressure. Yes, isobaric means constant pressure, but here it's isochoric. It's isochoric we're dealing with. Okay. Now, this is question 12. Let's take question 11. Yes. Question 11 we have already done, okay? If you remember, we've already done question 11. I'll do it again quickly, okay? And then I'll set you free because the previous ones we've done for sure, and we spent, I think, enough time doing them. So we're dealing then with a 90 kilogram man here. 90 kilogram man climbing to reach the top floor of the building, a total change of height 20 meters, of 20 meters. As a result, he uses up 20 kilocalories. So reminding you, 1 kilocalorie with a capital C is 1,000 calories, of course, and 1 calorie with a lowercase c is 4.184 joules. For short, you can say 1 kilocalorie is 4,184 joules, just to keep it short. Now here, in this case, we're asking you how much, or this is, he uses a 20 kilocalories of stored food energy. Sorry, I forgot to mention that. How much heat must his body dissipate? Now, again, here we're looking at this man here. Man is here, and he's trying to climb, okay, stairs in this way, something like this, etc. And it's 20 meters high. This way, so this is all 20 meters high. Okay, he gets to the top of the building, etc. So if we consider the system here, okay, man, okay, in his environment as an isolated system, okay, so it's going all the way up from here to here, right? So the internal energy of this system will remain constant. So whatever energy exchange happening in the system will remain in the system, and nothing comes from outside. So if that's the case, the total change in internal energy, delta U, will be equal to 0. Okay, and this is the 0 here, and it corresponds to the changes in all forms of energy, including kinetic, delta kinetic energy, plus delta potential, plus delta thermal energy, plus delta food energy. Okay, now kinetic energy, change in kinetic energy will be 0 because initially he starts from 0 and he ends with 0 kinetic energy. Okay, he doesn't have speed when he reaches the top. Okay, now sorry I'm taking a bit longer, guys, so I'll be done quickly. Then we have a change in potential, mg delta y, plus change in thermal, that's my unknown, and plus minus 20 kilocalories. That's what is lost in the process as food energy. Okay, that's lost in the process. That's why I put a negative sign. Now plug in the numbers. This is for mg delta y. Delta thermal energy, that's my unknown. The 20 kilocalories converted to joules. Okay, so first I multiply by 1,000 from calories with a capital C to calories with a lowercase c. And then you multiply each calories with a lowercase c by 4.18. And you end up with these values for potential, this value, okay, for the food energy. Solve it for delta thermal energy, you end up with a thermal energy or heat energy that must be dissipated equal to about 66 kilojoules. Okay, and that's your option B in this case. Right, so that's all for today. Okay, now the previous questions we've already addressed, okay, before. If you check all the previous recordings, we've done question 10 backwards to the first question. So we're done with midterm 2018. Now, questions from 2017 are pretty much the same. Okay, so pretty much the same. Now, I may be on Zoom later or tomorrow afternoon. So if you have any question, feel free to join. Ask me more questions. Otherwise, please drop me an email and I'll be more than happy to answer. Right. Thank you very much, everyone. So I'll stop here for today and all the best for the midterm. Okay.
Thank you, Doctor. Have a nice